Hello, welcome to Chapter 3, Analyzing and Representing Data with Measures, Part C, Measures of Spread. To understand the importance of the measures of spread, as known as variation, variability or dispersion, let's work on exercise 1. You are the manager of a soccer club and you can hire one of two players. Player A has an average of 1.6 goals per match, GPM, and player B has an average of 1.4 goals per match. Let's assume that the values of the other main variables, price, etc., are the same. Question 1. Whom would you hire? Why? By now, the answer seems obvious. Player A, because his average GPM is higher. We want players to score as many goals as possible. Question 2. Now you have access to the player's record. Here we work with 5 matches to keep it simple, but we could be working with 50 or 500 matches. This is the distribution of number of goals of the two players. Looking at this information, whom would you hire? Interestingly, most people agree that with this new information we should hire player B. The reason that people usually give is that player B is more consistent, more dependable, more predictable. I like these adjectives, and I agree. It almost seems that player B guarantees at least a goal per match. We don't have so much certainty with player A, and you know that in soccer one goal means a lot, so we probably can win more matches with player B than with player A. Player A could be the typical gifted guy with little discipline, while player B could be more moderately skilled but with greater discipline. We don't know, but certainly I would hire player B, and I would recommend more a record like player B's. This consideration that we have just done about the variability or volatility of player A is what we try to quantify with the measures of spread. In this exercise, we got our conclusion by just looking at the table because it contained information about only 5 matches. If we had the record of 50, 100 or 2000, I don't think we could get any conclusion by just looking at the table. We need to be able to measure the instability or variability of the data in an objective way. In this question 3, we introduce and explain the 4 most famous measures of variability. We will see that all of them agree that player B is more consistent. The easiest one is the range, defined as the maximum minus the minimum. So for player A it is 4 and for player B it is 1. The problem with the range is that it is based in the 2 most extreme values. We can get a more resistant and a more loyal measure of spread if we consider only the middle 50% of the values. We call this the interquartile range, IQR, defined as the difference between the third quartile and the first quartile. If you look at a box plot, the IQR is the length of the box. Let's get the quartiles quickly with the help of the scheme. For 5 positions, the scheme will be 2 in the left, 2 in the right, and 1 in the middle. So the median will be in the 3rd position. If we focus in this first half with 3 individuals, the scheme will be 1 in the left, 1 in the right, and 1 in the middle. So the first quartile will be in the 2nd position. Therefore, the 3rd quartile will be in the 2nd position from the right. For player A, the number of goals are 0, 0, 1, 3, 4. Remember that we must sort them increasingly. For player B, the number of goals are 1, 1, 1, 2, 2. These are Q1 of each player and Q3 of each player. Therefore, the IQR for player A must be 3 minus 0 equals 3, and the IQR for player B must be 2 minus 1 equals 1. The next famous measure of spread is the variance. The variance works with the concept of distance from the mean, which we introduced in part A of this chapter 3. Probably you agree that the distances from the mean of all the individuals give us a measure of how dispersed the values are. So we could think of averaging all the distances to get a measure of that dispersion. But there is one problem with this. We saw in part A that the positive distances will always cancel the negative distances. Thus, the average of these distances is meaningless because it will always be zero. The variance fixes this by squaring every distance. You can see this in the formula. The value of each individual minus the mean, this is what we call the distance from the mean or the deviation from the mean, squared. How do we average all these squared distances? Adding them all together and dividing by the total number of them, n. Notice, however, that here we don't divide by n, but by n minus 1. What happens is that there are two formulas for the variance. One is preferred for samples and the other is preferred for populations. This version with the n minus 1 is preferred for samples, and the version with the n is preferred for populations. Since most datasets can be considered samples, that's to say parts of a larger population, it's common that books work only with this version of the variance, the n-1 or adjusted version. Here you see the formula applied to player A. The first value of player A is 0. From 0, we subtract the mean, 1.6. This is the distance from the mean of this first value. We square it. And now we multiply it by 2 because there are two individuals whose distance from the mean is this. The second value of player A is 1. From 1 we subtract the mean, 1.6, and we square this distance. We do the same with the 3 and with the 4. We add all these square distances together and we divide by the total amount of individuals minus 1. When you solve this, you will see that you get 3.30. If we do the same for player B, we get a variance of 0.30. Again, we confirm that player A is much more dispersed than player B. There is something here that could look weird. If the variance measures distances, how can we have an average distance of 3.3 in a situation like this, where the values are from 0 to 4? You may think that this 3.3 is an exaggeration of the actual distance. If you are thinking this, you are totally right. The variance inflates the distances by squaring them. Technically, we say that the problem of the variance is that it works with squared units. For example, if all the values are in feet, the variance will be in squared feet. How can we fix this? We apply the square root. The square root of the variance is what we call the standard deviation. By applying the square root, we return the size of the measurement to its original dimension or scale. The standard deviation of player A is 1.82 and the standard deviation of player B is 0.55. The standard deviation is by far the most used and most famous measure of spread. We will be working with it all the time. The Latin S and the Greek S, the sigma, are the two common notations for the standard deviation. Sigma is commonly used when we put n in the denominator and S when we divide by n-1. In other words, the sigma is for the standard deviation of the population and the S is for the standard deviation of a sample. Exercise 2. Up to now we have been speaking of outliers in qualitative terms. Now we are introducing a criteria to determine numerically which individuals must be considered outliers. It's called the 1.5 IQR criteria. The idea is simple. Those individuals in the middle 50% of the distribution can never be considered outliers, because the middle 50%, that's to say the interval from the first quartile to the third quartile, is precisely the common place to be. So we are going to take this middle 50% as a reference, and we are going to use a tolerance of 1.5 IQR above and 1.5 IQR below. If a value is farther above or farther below than that, we label it as outlier. Many books call these limits the left fence and the right fence. So the left fence equals first quartile minus 1.5 IQR, and the right fence equals third quartile plus 1.5 IQR. In the particular case of player A, the left fence is 0 minus 1.5 times 3. This equals negative 4.5. The right fence equals 3 plus 1.5 times 3. This equals 7.5. Player A does not have any match with more than 7.5 goals or less than negative 4.5 goals. This wouldn't even be possible, so there aren't outliers. Exercise 3. In the same way that we used a box plot to graph the 5-number summary, we can use a hat plot to graph the mean and the standard deviation. We mark the mean, and from the mean we go one standard deviation to the right and one standard deviation to the left. This will be the box of the hat plot. In this case, about goals per match, the left side can begin in 0 because the negative values would not make sense. The right side finishes in 3.42. And now we connect this box with the maximum and the minimum. Notice that we are connecting this box with the maximum from the bottom, not from the center as we would do in a box plot. That's how we tell at the first sight a box plot from a hat plot. And that's why we call this graph a hat plot. In many cases, it really looks like a hat. This example of the football players illustrates the importance of complementing a measure of center with a measure of spread. The good practice that you must acquire now is, when you get a measure of center, be sure to also get a measure of spread. The smaller the measure of spread, the more meaningful the measure of center, and vice versa. The greater the measure of spread, the more meaningless the measure of center. Player A has a great mean, but his mean is not very meaningful because he also has a great standard deviation. If you are measuring the center with the mean, you should use the standard deviation as a measure of spread, and you can graph both in a hat plot. If you are measuring the center with the median, you should use the IQR as a measure of spread, and you can graph both with a box plot.